Welcome again, and thank you everyone for attending today's webinar, Using Metrology Software to Capture Data for Reverse Engineering, brought to you by Design World Magazine. I'm Leslie Langnaw, Managing Editor, and I'll be your moderator today. And I'd like to introduce you to our presenter, Les Baker, and thank him for being here today. Just a couple of housekeeping details before we get started with the webinar. If you wish to tweet about this webinar anytime during or after, please use the hashtag DWWebinar. Also, we will have a Q&A session at the end of the webinar, and this webinar will be made available to everyone afterwards. It will be emailed to you, and it will also be available on our website. Within this presentation, Les will have a couple of poll questions for you to answer, so be on the lookout for that. But you can go ahead and submit any questions that you might have, or anytime during the webinar. There's a Q&A box for you to enter your questions in. Go ahead and do that whenever you want to ask a question, and we will address it at the end of the webinar. So Les Baker is Senior Applications Engineer for FARO. He provides expansive technical and applications support. He is a master at breaking highly technical concepts down into bit-sized chunks, so even the most technically challenged among us can digest and use them. Previously, he was a physical education teacher, but he's been with FARO for 6 years now, and he is passionate about making an impact on the lives and businesses of the folks that FARO serves. So without much further ado, I'm going to hand over the mic to Les.
Hello, everyone. Welcome. Just a little technical issue there, I believe.
Got control of the slides, Les?
Yeah, I believe it's missing out one of the slides. But welcome to today's presentation. My plan is to look at examples of the techniques and aims that gave birth to what we now know as reverse engineering, and to see how easily and successfully it can be accomplished with the minimum disruption to your current workflows. Understanding these nuances will help with cost justifications to the basics initially, but if necessary, for additions to improve efficiency down the line, or maybe even straight out of the gate. So with your permission, let's get started and find out more. The presentation is split into several parts. With what is reverse engineering, we'll take a brief look at the evolution of RE and review some of the different end goals that could legitimately fit under the reverse engineering umbrella these days. For a reverse engineering example, we'll take a stroll through an actual application and see what can be achieved with a little brute force and ignorance, i.e. a portable CMM, some 3D inspection software, and some CAD software. The minimum requirement to live this particular dream. This will help you determine if it's the most efficient method for you, or if you should consider adding extra hardware and software. Talk is cheap, so in the brief demonstration, I'll show just how quickly and accurately you can capture the geometric features and free-form elements of your part and report them and export them for use as the framework for modeling in CAD. And then we'll finish up with a summary. I'd like to say thanks to Ricky Swain, who's an engineer with Andritz Igerson Tools, for supplying some of the content for today's presentation. And as mentioned by Leslie, the presentation has an audience participation element which takes the form of a series of polls, and our first question is about to arrive. And the question is, were or are you intimidated by the myriad choices you're faced with when considering implementation of reverse engineering? And there are four answers. Yes, it seems to involve adding even more specialist new software. Yes, there'll be a productivity gap and a steep learning curve across several disciplines as we ramp up. Or yes, it would be easier if we could take a step-by-step approach, adding more capability later if we needed, or just a plain no. So I'll give you some time to enter your responses, and then we'll review what everybody answered. So everybody's still voting. So everybody, or the majority of people, I should say, seem to think it would be easier if they could take a step-by-step approach. So hopefully this webinar is really going to help today. So to continue, what is reverse engineering? Wikipedia, which is the fount of all knowledge these days, tells us that it's the process of extracting knowledge or design information from anything man-made. And then it describes a whole series of other things that we may need to want to reverse engineer about a particular part or process. In the picture, in the slide, there's an example of reverse engineering with a scanner being used to capture data to document the as-built layout of the plant, process, and piping within a factory, perhaps to assist with reverse engineering of modification or repairs. In measurement terms, we're really just interested in the actual dimensional aspects of the part in question. So we slimmed down that Wikipedia definition. In this image, you see a laser tracker being used to reverse engineer a large, extremely high precision machined part. Sometimes we may not want to carry out an engineering function using the data we've gathered. We just want to understand what we ended up with after the manufacturing process because the part doesn't meet print, yet it functions anyway, or vice versa in some cases. Without modifying the manufacturing process, we can just use those dimensions as the design data to inspect future parts against so we can be sure they'll function, rather than modifying the part to meet the print and finding that it doesn't work anyway. The data can be immediately incorporated into your inspections, but simultaneously can drive your engineering change request system so that your part always reflects the CAD model that everybody is using. Reverse engineering is considered by some to be a comparatively new thing, perhaps spurred by the recent move towards rapid manufacturing. But in reality, it's been with us as long as people have needed to design, manufacture, or copy things. And computers have certainly made that easier over the years. In this image, we have a computer-generated animation of a quarter-scale clay that's being scanned by a laser probe mounted on a portable CMM. Even the newest designs incorporate some legacy components that may predate the CAD that is so prevalent these days. We document the as-made condition of these parts or mating assemblies so we can be sure it'll actually integrate as intended, rather than just designing to the ideal dimensions in the print that the part may actually deviate from anyway. And that just causes costly redesign and rework. I think this image just shows an example where reverse engineering perhaps has met over-engineering. There's not many planes would still be in the sky as comfortably as that one without its tail. There are situations where damaged, worn, or even new parts need to be repaired or optimized in order to function as efficiently as desired. These modifications need to be applied and incorporated into an updated design so that the future parts work right out of the gate. If we think of the blades of jet engines or the bodies of cars, they go through iterations of wind tunnel testing, followed by modifications to improve their aerodynamics. But every modification needs to be captured and then fed back into the model. Sometimes this as-made data isn't needed so the part can actually be manufactured, but may be used to establish an accurate CAD model of an existing legacy part so that virtual testing, such as finite element analysis, can be conducted, reducing development and potentially warranty costs. If that legacy component wasn't strong enough to carry over to the new product, we don't want to find out the hard way. An example of this is making a car door out of lighter materials, but still able to meet tougher crash standards as the years advance. We can see that reverse engineering is just another way of applying measurement data to manufacturing. It makes sense then that we should be able to use our metrology tools and inspection software to acquire the data, and then our design software to incorporate that data. And here we see a full-sized motorcycle concept clay being scanned by a 3D imager. So time for another poll. Does your company currently reverse engineer? The responses here are no, we haven't considered. No, but we're beginning to consider. No, but we've begun analysis to quantify the benefits. Yes, but we didn't realize we were. Or yes, it's an essential part of what we do. So we'll take a moment for everybody to get their responses in and then review the stats. So the majority of people seem to be fully on board with the reverse engineering concept. A few of you are reverse engineering without knowing that's what you were doing. Some haven't considered it, but some of you are considering it, and some have begun the analysis. So again, hopefully the information contained in this webinar are going to be useful for you as we proceed. So we'll move on to our reverse engineering example. Reverse engineering in its simplest form could just involve traditional 2D metrology tools used to acquire dimensions to modify drawings. But that's a world we inhabit less and less these days. So let's see how it's been updated to the 21st century. Andret Sigerson, a company down in Florida, used the 3D data from inspection software on their portable CMM to record as-built information from internal and OEM machines in order to reverse engineer superior repairs and replacement parts. You can see their portable CMM in the picture. It stands about 3 feet tall to give you a sense of scale of the part that's being worked with here. The part does look very complicated, but in reality, it's just a collection of geometrical elements. Planes, circles, cones, cylinders, etc., plus a few free-form surfaces that are all easily captured with the CMM. If we zoom into the detail in the pockets on the part of the previous picture, we can see that geometry a lot better. Here are some similar geometrical elements captured on the chipper disk from the earlier slide, and those measurements that have already been taken in the inspection CMM software have been imported into CAD. So all they've done is they've captured the center of rotation, the OD, the ID, and then all the information that's in one of those pockets. That actual data acquired by the arm is used as a template for the CAD geometry and copied and rotated the appropriate number of times to complete all the detail within the disk. This allows the new part to be engineered from the old, designed to the actual dimensions of a known working part. Just like that dentist can design you a crown from a broken tooth. The initial samples can then be checked against the new CAD model using the portable CMM and inspection software, completely closing the loop on the design and manufacture of that part. And both the correctness of the geometry and the freeform surfaces can be verified. Points have been measured and they're automatically compared against the CAD surface, and the color map is created to show where those points are relative to the surface. So Andritz Iggesund used their portable CMM as an inspection tool for product verification. Separately, they used CAD to design their products, and their reverse engineering capability was a happy marriage of two technologies in which they were already competent. They didn't need to add anything else to their workflow. Following on from the last question, where one of the answers suggested that there might be a productivity gap as you ramp up the techniques, would you consider using a service bureau to keep any productivity gap manageable? Simple answers to this one: yes or no. And again, once everybody's entered their responses, we'll review the results and move on. So it's almost split 50-50. Some of you would use services as they ramp up, and just under half of you wouldn't. So there are so many CAD plugins and standalone software packages available today, but they may or may not have relevance to what you're trying to do. It's important to understand your requirements using the simplest workflow possible, so you can more clearly realize the ebbs and flows of advantages and disadvantages that adding extra modules could bring. Justification of additional models to aid efficiency in future is easier when it's based on real experience. So not knowing what your requirements are first when you go to buy a car makes the process longer, possibly more exhausting, and potentially more expensive. And whenever you have any of those things in play, it can make you much more susceptible to buyer's remorse. So I'll finish up today by showing you a brief demonstration of just how quickly and easily you can acquire and export the measurement features in a format that can be handled by your CAD. You'll also see how point cloud from a laser scanner can easily turn those free-form surfaces into a format that your CAD can handle very economically and integrates nicely with existing CAD techniques. Sometimes some of the specialist reverse engineering add-ins may not be quite as efficient and may not quite work quite as well with those existing CAD techniques. So here we have a picture of today's part, the portable CMM that I'll be using, which has a contact probe and a non-contact laser scanning attachment, and also the 3D inspection software that will facilitate data capture and processing of the non-contact and the contact data. So now I'm just waiting to take control of the screen so that I can show you my inspection software. And here we are. The first thing I'm going to do is take advantage of the capabilities in the inspection software to template some stuff in there just to make it easier for me. So in this program, I've already added some of the features that that I want to measure to make it easier for me as I speak. So I'm going to measure a plane on the left-hand end of the part, and all I'm doing here is touching the probe against the part and recording points on the plane and then in the ID so that the software automatically makes that geometry. But run across to the other end where I can measure the other end plane. And again, the ID. Now I could measure more or less points. It's entirely up to me. There are some bosses that are mounted radially on the part. I'm measuring those now, just the plane. And as I go, it's building up those features within my file. I'm also using these features to create a coordinate system, a frame of reference with a defined 0, 0, 0 and with a defined 0, 0, 0 and axis orientation to make it easier for me to work with this part when I bring it in, because my X, Y, and Z are all defined. So you can see my X-axis is running through the middle of my part. My Z-axis is going up through one of the radial bosses, and the 0 is in the center of the ID at one end. So makes it really simple for me to see what's going on with the part. Now I'm going to add some more features. I'm going to measure a couple of cones on the end caps of the part. Again, using the contact capability of the device. To just quickly capture and define the sizes of those features. And this time you can see that I'm actually telling the software what I want to measure as I go along, rather than using the templating capability. One of the things that I've done that you can probably see in the image that I gave earlier was that I'd stuck some putty onto the part so that it's not perfect, so that there are some flaws on the part. And the beauty of probing is that I can avoid those flaws, and it's going to give me a perfect representation of that feature without dings and dents and flaws in it. Okay. So you can see that one of the nice things about the software is that as I probe the things, if I probe to the length of the feature that I'm interested in, it actually gives me a reasonable visual representation of the part that I'm measuring. So there's some cylinders. I'm going to measure a few more planes. Now, the end caps of my part are actually made of bolts that are welded on. So I get these bolts in the right place. What I'm doing is that I'm measuring these planes just as a reference for the location of the bolt. I'm not going to use these planes to actually model the bolt, because the bolt is already a stock component that I can call up from a library. So you can see here that very simply I can just quickly capture those planes, and I'm going to know exactly where that bolt should sit. So I think you'll agree that it was pretty quick for me to go in and capture the data on here. What I'm going to show you now is how you can add readings to a point cloud and actually using the laser scanner and actually capture data on freeform surfaces. Okay, so seamlessly I can switch over to the hard probe, sorry, to the laser scanner, and I can just capture data on my part. So you can see that very quickly I'm capturing loads of points on the surface of this part. Basically 2,000 points 280 times a second. One of the things that I did was I measured a plane on the surface of the table and used that as a clipping plane so that it didn't capture any data physically on the table, which saves you a lot of time afterwards where you've got lots of extraneous data, you need to go in and delete that data out. So you can see how complete that part looks, the image looks. You just look at where there are holes in the data, and then you can just go back in and scan them if that's necessary. But like before, this is going to be reference data for me to make sure that a stock part that will assemble to this model is in the correct place, rather than actually modeling from this information. So one thing that some of the third-party reverse engineering packages that specialize in reverse engineering can do is that they can take this point cloud and they can turn it into a polygon model, and you can export that, bring it into your CAD, and use it as a basis for modeling. But some CAD packages don't handle a lot of points very well, or they don't handle polygons very well. So that can be it can be a drawback. The beauty of the inspection software is that it enables us to cut cross sections in this data, and CAD copes with curves and polylines and things like that very, very well. So by filtering the data down using cross sections and curves allows us to get this data into CAD very, very effectively and very, very economically. So I'll show you how we can cut some sections in here. So I'm going to construct a cross-section scan from the scan that I created already. And because I've aligned this to CAD, I can take advantage of that by using one of my coordinate system planes to cut a section plane through there. So I'm going to use my XY plane through here to cut just one plane. And if I hide the point cloud, what we'll see is there is my section curve. It's a line of points that follows the surface of the CAD model. And you can see here that here's one of those pieces of putty that I glued on here, which if I polygonized this and took it into CAD, it would take a lot of cleaning up to get rid of that feature. But on here, I can literally, when I get into CAD with the polyliners, cut this section of the curve out and repair it, and within 30 seconds I've got a good curve on there that I can then rotate around the center axis of the coordinate system, or the center of the cylinder, and create the body of this, the unblemished body of this particular part. So it can save you an awful lot of time using cross sections rather than going to polygons. Also, rather than cutting just one section, I would usually cut a couple of sections so that when you do revolve it, you can see that you've got your center of rotation right, so that the surface rotates through every single cross section. That one cross section rotates through all the other cross sections. If it doesn't, then that's a sign that your axis of rotation isn't in the right place. So another thing that we can do is cut lots of cross sections. Again, let's go in and cut some more sections. This time I'm going to use the YZ plane of the coordinate system, and I'm going to tell it that I want my cross sections to be 2.5 millimeters apart, up to 30 cross sections. So you can see that there are all those cross sections that I've cut through there. Let's hide some of the geometry so it's easier to see. Let's get rid of that cone as well. So you can see that there are all those cross sections. If I tried to bring in that model that was made up from polygons from all the points, there would be a massive amount of data here. But you can see by thinning this down just to these lines, I can still see enough of this part to model it. You can see that the first curve that I created could be a loft curve that sweeps through all these individual sections. The nice thing about revolving the part, particularly circular parts like this, is that I don't need to have all the data that's down here. In order to scan this, I would have to fixture it so I could see all the way around it if I was going to use some of the reverse engineering packages that are available. But if I'm just going to revolve this section, I just need to scan it along one section and know I'm going to be good to go. So let's have a look at how simple it is to export this geometry then. I can just, if I want to export the cross sections, I can simply just highlight them, go to File, Export. I can export them as points, or I can export that measurement data to CAD. I prefer to export the measurement data to CAD. You can see that everything that I was selected is in my export list. I'll click Next and choose the particular format. I'm going to go for IGES and perhaps millimeters. I then just need to choose where I want it to be. And allow those to export. Quite a lot of data there, so it took a moment or so to finish. And then once that's complete, I'll go on and export the rest of the geometry, the geometric features. It's a very similar process. I think we're just experiencing a lag because of the nature of handling all this data over a webinar, but once it's once it's finished, I will I'll continue.
Yeah, it does take a minute or two to go during the webinar.
Yeah, it's coming back now. I can see the the status bar actually moving now.
Just a reminder for everyone, go ahead and type in your questions that you have for Les.
Data's traveling quite a long way. I don't know if it gets air miles for this, but apologies for this. It certainly was a lot quicker when I wasn't attached to the webinar software this morning.
On average, Les, do you know how long it might take to translate some of that data?
Well, this morning I played around with this morning, and it literally took 30 seconds to export.
Okay. Are there any special hardware requirements, or any computer will do?
For the inspection software, with the laser scanners these days that can acquire such a vast amount of data so rapidly, you want to be at the top end of the laptop range of computers. You can get a lower spec computer that will do, but it just won't be as efficient. You would probably have to scan your part in smaller segments. You might even have to split it into several files. I think I'm going to cancel that so that I can have the computer back, and then we'll try and complete the presentation. But that's
Before you go back to the presentation, there is a question that came in that might be relevant to this, and the question is, are you going to make a solid part out of these data?
Today, no, I'm not. This is purely about, today is purely about capturing the data for use in CAD.
But you could make a solid part.
Yes, yeah. The whole premise of this is, and you could see from earlier in the presentation the images from Ricky were showed how that data can be modeled. You're really just collecting the template information that you're going to use in CAD.
Okay.
And so I click cancel, but there's not much sign of anything else coming back. So I'm going to, I think what we'll do is, what I was going to do was show you how to export the other geometrical features, which was exactly the same process. I would have just selected the features that I wanted to export, said file export, and exported them to a separate IGES file. And in your CAD, you'd have imported the sections as one IGES file, the geometry as another IGES file into the same file, so that you would have everything that you needed to create the model. So what I think we'll do is call it the end of the demonstration, and now move back to the presentation. if that's okay.
Yeah, we'll get the slides up for you.
So I had the foresight to go immediately back to an audience poll in case we had any technical issues. Unfortunately, the technical issues occurred before we got there. But the question is, has any of the information presented given you any new perspectives on implementing reverse engineering? No, it reinforced what I already knew. I was familiar with most concepts, but there were a few new angles, and it was all new. So once everybody's got their responses in, again, we'll see what everybody thought. So it seems that for the majority, you were familiar with most of the concepts, but there were a few new angles. For 30%, it was all new. 18% of you have been around this industry for a while, I think, and then for another 6%, you've been around even longer. So finally, in summary, reverse engineering has been around a long time in many forms and is here to stay. It has as many goals, and as many techniques, and is constantly evolving. The possibilities of reverse engineering are limited only by your imagination and the amount of money you want to save. But as we're all aware, saving money usually involves spending some too. And finally, understand intimately what you do currently so you can investigate thoroughly how the technology you're exploring can best complement that. Thanks very much for your attention today, and I look forward to seeing you out in the field at some point in the future.
Great. Thank you very much, Les, for an interesting presentation. We do have a few questions, and if you're ready, I'm going to start those right now.
Sure.
Okay. If you were measuring a bearing, what would the accuracy be?
That would depend on the type of device that you would use to measure the bearing. There are so many things that come into play when you're measuring a bearing, particularly a large bearing. The individual points that you measure will be very accurate, perhaps to within thousandths of an inch. But sometimes the points that you don't measure are as important as the ones that you do. So if you can capture a lot of points, particularly using the hard probe, then the geometry that you create is going to be very, very accurate, and you're also going to be able to investigate the form of that cylinder or circle, however you choose to measure it. So you can get a good feel for whether the accuracy that you're getting is truly representative. If the form is bad, then that means that either the fit of the points is not good, or the cylinder that you're measuring is not good. So it gives you a lot of flexibility to get the data that you need and to understand your part more effectively.
Okay, another question that has come in if I have a scanning CMM and I did a 2-scan of a CAM profile that generated a point file, how can I convert that to dimensionable geometry in 2D AutoCAD?
In AutoCAD, you could possibly export that information as DXF. So to go into AutoCAD, I would export that as a DXF and take it into AutoCAD as a DXF, because DXF does support polylines and polygons as well.
Okay. Does FARO offer trial versions?
Yes.
Of some of these programs? Okay. This gentleman was asking specifically about CAM2 Measure 10.
Yes. If you go to FARO.com and go to the products page, there's and look for the CAM2 Measure 10 software, you'll see there's a link there that you can download an evaluation copy. And
okay.
I believe the eval license lasts for 45 days.
Oh, okay. Back to the question about whether or not you were going to make a solid part. There's a part 2 to that question, and the question was they were curious about the process of getting the solid part files created. Could you go into that process a little bit?
Well, yeah, I mean, that you would use your CAD software. You know, there are so many different options out there. For example, I know that Andrew Sigerson used SolidWorks. So they import that geometry into SolidWorks, and it comes in as planes, as cylinders, as cones, as circles. And you would just model with it in the way that you would model as if you were modeling something from scratch. You know, you would use those circles and planes as the basis for your sketches.
Okay, and one more question that's come in is, are you willing to talk about the cost of the setup that you used?
I'm an application engineer, so I try and stay as far away from how much things actually cost as I possibly can. But the ballpark figures, and hopefully my bosses aren't listening. You're talking within the 50K kind of range for the arm on its own. You're probably talking within the 20 or 30K range for the scanning attachment, and then the inspection software is less than $10,000.
Okay. Well, if there are no more questions, Les, I'd like to thank you again for a good presentation on how this reverse engineering software operates and what FARO can offer. And I'd also like to thank everyone on the webinar who attended. Just a reminder, you will be emailed a copy of this webinar for you to view at your leisure again, and it will also be available on the designworldonline.com website. Again, our hashtag is DWWebinar, and if you would like to continue a discussion of what you learned here, please feel free to go to engineeringexchange.com. You saw Les's email and phone number on the previous slide, so if you want to connect with him off-site, please feel free to do so. So thank you all again for attending this webinar.